So in this diagram, the y-axis here is energy, and we can think of it as free energy. And then you've got on the x-axis some kind of reaction coordinate that describes progress along a certain coordinate that you define. And often there are, actually maybe that's not even the best way to talk about it. This is 1 degree of freedom. This might be bond length, or it might be rotation around a certain bond. It's a change in geometry. And this on the y-axis is another degree of freedom, another separate change in geometry. And so you can see that if, for example, we were talking about bond rotation, one of these would be a dihedral angle, and then we might on the other axis have bond length or something like that. In a molecule with n degrees of freedom, and that can be translation, meaning moving around in space. This can be tumbling. It can be bond stretching. It can be bond vibration. It can be bond angle distortions. If you have n degrees of freedom, your potential energy surface is going to have 3 times n minus 6 dimensions. So, in a molecule that has a ton of atoms, we rapidly get to the point where we can't think very clearly about what this potential energy surface looks like. But if we reduce it down to 3 dimensions and just think about it in that way, we can get a sense for the shapes and the features of this potential energy surface. So each point on this surface represents a particular molecular geometry. Okay, and you can think of it, we don't even need to think about a reaction in this case. This could be a conformational rearrangement. One element of geometry here, another element of geometry there. We have high points, peaks, and those are almost never traversed. Okay, we have low points, which are energy minima, and these energy minima can be either products or starting materials, or they can be intermediates. And the change in free energy for a reaction is just going to be the difference in free energy between those minima. Now, you've heard of transition states, and you've heard of them as the high point along a reaction energy coordinate, but it's a bit more complicated than that, because the transition state is going to be a saddle point on the potential energy surface. In other words, it's going to be the lowest energy maximum. That doesn't make a lot of sense, but do you see how it's higher in energy to go this way than it is to simply go that way? Right? So we're going to traverse the lowest energy pathway from intermediate 1 to intermediate 2. And we'll talk actually about that. We have some wiggle room in terms of how we traverse that pathway. But saddle points are going to be our transition states. So and so a lot of things that you might get from, so we'll call this a less likely pathway and this a more likely pathway. A lot of the intuition and principles you might have from like hiking in the mountains sort of apply here, and some of the same terminology applies. Like there are saddle points in scaling mountains and hiking, and typically, unless you desperately need to get to the highest point to say that you did, if your goal is simply to get from point A to point B, you're going to choose the least energetically costly pathway. Okay. So at the saddle point in the transition state, there's some important features that we need to be aware of. We sometimes call the structure at the saddle point the activated complex. And at this point, you have equal probability of going forwards versus backwards. And we need to actually talk about the energetic features of both the minimum and the maximum, of the intermediate and then the saddle point, the transition state. All right, so let's look at that intermediate. And imagine from this intermediate geometry, we make some kind of displacement either along the y-axis or z-axis. Okay, either in this direction or this direction. What do you notice as we displace the molecular geometry from its minimum value? What does energy do? Any way I go, it's up, right? That's the definition of a minimum, is that any other way you go from there is up. So one of the things you can do to define what those energy minima are is that the slope of energy with respect to whatever these coordinates are is positive. Okay, and so we might say that one thing that characterizes the minimum, first we would say that the first derivative of energy with respect to whatever these coordinates are has to equal 0, because that's how we find minima in calculus, right? That's where the minimum is where the slope is 0. But then the other feature of the minimum is that the second derivative is positive in all, if it's an energy minimum, the second derivative has to be positive in all directions, in all dimensions. And that's how you tell that something's minimum, because if you make a displacement, the energy goes up. So, and I guess, I don't know, I didn't explain that particularly well. Remember, the second derivative is how the slope is changing. So if you're at a minimum, let's just look at a slice of, let's look at this particular slice of the energy minimum, and we'll have energy on this axis, and then we've got the another degree of freedom. We have something that looks like that, and this is our energy minimum. At that minimum, the slope is 0, but the slope has the second derivative would have a positive value here, because the further away you get from that minimum, the more the slope is increasing. Get that? Yeah. Now, one question you might ask is, how could you tell mathematically a minimum from a saddle point? Because the saddle point is a maximum, right? If we were to take this particular slice for our transition state, here's our energy. I don't need that. Sure. Here's our energy, and here's our first degree of freedom. And if we look where the saddle point is, that's at a maximum. And of course, at a maximum, the first derivative is 0 too. So how do you tell maxima from minima? Well, notice even though at the saddle point, the first derivative with respect to whatever this degree of freedom is equals 0, what do you notice about the second derivative? It's negative, right? Because the slope is decreasing, right? So one of the things that that characterizes maxima is that the second derivative is greater than 0. Now, we got another problem, right? Because if we define saddle points as being first derivative equals 0, but second derivative is greater than 0, what? Yeah, sorry. Thank you. Thank you. Is that right? Good. If we define saddle points as having second derivative equal to, or rather less than 0 negative, how do we distinguish a saddle point from the peak, right? Because at the peak, second derivative is less than 0 in all possible directions, okay? So let's, shoot, I kind of want to copy this image and move it down so that we can erase some of the things. And maybe draw, erase some of what I've written here. So that we can sort of zoom in on one of these saddle points. So yeah, our question is, what makes the peak and the saddle point different? Notice that at the peak, we go down in all possible directions. So at the peak, the second derivative with respect to whatever our reaction coordinate is less than 0 always. In all dimensions. But look at the saddle point. If I go in this direction or that direction along, say, and let's just for the sake of our argument here call this x, this y, and this z. And this will be energy. At the saddle point, one of the things I notice is that d, the second derivative of energy with respect to x, is less than 0. But how about in the y direction? If I move in the y direction, I'm going up in energy, right? So that's actually what defines a saddle point, and that's how you can identify a transition state, is that at a transition state or a saddle point, the second derivative with respect to yeah, right. The second derivative, I don't know how we're going to do this. Let's see, dimensions. Let's call, yeah, there are n dimensions, x, y, z, etc. And so any given dimension will be n, I don't know. The second derivative with respect to all the dimensions has to be greater than 0, except for 1. So in this case, only the second derivative with respect to our x-axis. And guys, I did it again, right? It has to be greater than 0 in all directions except 1. Okay? At a saddle point, it's in moving only in one direction and only one direction that.
I think your switch should be less than 0, not all dimensions.
Okay, so it's greater than 0 in all dimensions except, in this case, x, where second derivative is less than 0. So I think I got it. Yeah. Okay, so what is this? Why are we talking about this? Well, this is what you do computationally when you're trying to identify a transition state, is you calculate the energy of your proposed transition state structure, and then you move it around according to all these possible dimensions, and you've got to find the structure where when you move it in all possible dimensions, the energy goes up, except for in 1. Okay? Another way of saying that, and there's some, I can show it to you mathematically, but we don't necessarily need to. Another way of saying this is that at the transition state, forces on a structure or the activated complex are all 0 except for 1, except for in 1 particular dimension. Okay. Whereas at the minimum, all forces on the structure are 0 in all directions. Okay. Not sure I did the best job on that. So, what do you want to? Any questions? What do you want to talk about?
So, because we have more like 2 maximum there and 1 minimum.
Yeah.
And so the first maximum will be the activated complex or what?
I'm sorry. So, you mean here? This?
Yeah, that is the transition.
This is the transition state in the activated complex.
Okay, so
what is this one?
Yeah.
Yeah, this one is a high energy geometry that is never accessed. Yeah. Because you don't need to get from one minimum to another. You simply traverse the saddle point. There's a couple of interesting terminologies that are sometimes used. This is the transition state. This is one of those saddle points. And the edge of that saddle is sometimes called the COL, the call. I don't know why. Maybe that's a mountaineering term. I tried to look it up and I couldn't even figure it out. So, but the call represents the variation in energy along every other dimension other than the one that gets you over the saddle point. And what this figure is intending to show you is the pathways that molecules may take when they're going over this saddle or this call. Here is the minimum energy pathway, but of course at any temperature we've got a range of energies that particles have, right? And so they may traverse this pathway not exactly over the minimum pathway, but they may have some wiggle room in how they go over that pathway. So there's some distribution of pathways that are traversed over this transition state, though on average, the lowest energy one is the one that, rather, the average of all of these pathways is the lowest energy one. The idea here is that even in the transition state, there is some, it's not a Boltzmann distribution, but there is some distribution of energies along this call. And so there's some variation in how we traverse that transition state. Okay, so we got that picture in mind. Let's now sort of review some of how we talk about kinetics. And we'll talk about transition state theory. And this is what Eyring is responsible for. So let's have the reaction A plus B goes to C. Let's define a few terms. A and B with the double dagger we're going to call the activated complex. This is what you have to get to in order for you to traverse the saddle point. So at that saddle point, this would be our activated complex. This would be A plus B, and this over here would be C. Okay, so, and the rate of the reaction, we could say the first derivative of the concentration of C with respect to time, that's how much of C is showing up at any given time, is equal to some rate constant times the concentration of A times the concentration of B. Does it look familiar? Yeah. But another way of saying this is the rate is related to some intrinsic rate constant times the concentration of the activated complex. So in this case, yeah, AB with the double dagger is the concentration of the activated complex. And this rate constant, K with the double dagger, is related to a vibration in the activated complex that takes you down the hill, takes you away from the saddle point. It's a vibration. In this case, the pathway from A and B to C is in the X dimension. So this would be some vibration in the X direction. I didn't understand that at all the first time I taught this, and so I used Gaussian to try to help me understand this, and I wasn't necessarily going to do. And we're recording, so I'm going to show you a transition state I calculated for the SN1 reaction. Maybe. Or rather, the SN2 reaction, I think, is what I wanted. Well, it would have been a good idea for me to think of this before I had to go search for the file. Ah. So this is a results file from a calculation I did, finding the transition state of the reaction between bromomethane and cyanide. And this looks like what you'd expect. Here's the leaving group, and here's the nucleophile. Though actually, if we were to zoom in, you would see that that's not exactly planar, right? You may have been taught in undergraduate organic chemistry that the transition state of an SN2 reaction involves basically an sp2 hybridized carbon. That's true if the nucleophile and the leaving group are coming in and leaving at the same rate. Of course, in this case, it looks like for the bromo leaving group, the nucleophile has to come in a little bit more than the bromo leaving group leaves. But there's some interesting things you get out of transition state calculations. Why can't I? Sorry, it was giving me trouble. So the question is that rate constant that we were talking about. This is the activated complex, AB double dagger. And the rate constant that describes how this reaction goes forward is related to the following vibration that I'm going to show you. So, results, vibrations. So this is the vibration that's calculated that we're talking about when we say a vibration that makes you move down the reaction coordinate. You can't necessarily see it because it's showing you, or it doesn't look like you would expect, right? If we would sort of expect these groups on the end to be moving, but frankly, to have them in sort of stationary and the one in the middle moving is exactly the same thing. Notice how with this vibration, the distance, we're changing the distance between leaving group and carbon versus nucleophile and carbon. So the frequency of that vibration is related to how fast the activated complex goes down the hill towards products. In Gaussian, actually, this is the way you confirm that something's a transition state. You look for this particular vibration. It actually has a negative or imaginary frequency, which I don't understand, but that's what we're talking about in transition state theory with this K double dagger. All right. So let me just stop that record. Okay. So that's the vibration we were talking about in a reaction, a vibration along the reaction coordinate. And let's see. And then there's a postulate of transition state theory that says actually the starting material A and B are in some kind of equilibrium with the activated complex. Now, that's just a postulate, and frankly, it seems ridiculous because you can't be in equilibrium with the transition state, right? You can be in equilibrium between minima, but not with a transition state. Nevertheless, this was an assumption that Eyring made when deriving this stuff, and you can actually justify it later. We'll say that the equilibrium constant between A and B is the big K double dagger. So we can now get a sense for what this equation means. The rate of the reaction should therefore depend on the vibrational frequency of the activated complex that goes to products, the equilibrium constant between starting materials and activated complex, and then the concentrations of the two starting materials. So what this tells you is the way we used to write rate equations, that rate constant has two contributions, right? One of the contributions, my eraser's too big. All right. One of them is related to the vibration in the activated complex that leads to products, and then the other is related to some equilibrium between starting materials and activated complex. Okay. So why are we doing this? We're doing it so that you can understand when somebody in the future says, we did an Eyring plot, you're trying to understand what on earth they mean by that. Okay, so there's just a little bit about, just a little bit more math, sorry. I'm trying to figure out what math is necessary and what math we can ignore. Okay, so all right, this rate constant, little k with the double dagger, it comes from the frequency of the vibration that we've been talking about, frequency of the vibration that takes the activated complex and moves them to products, and some term kappa, which your text describes as a transmission coefficient. This can have values from 0 to 1, and it relates to the fact that not every time we get to the activated complex do we go on to product. So I don't know why I'm writing it this way. Not always does the activated complex go to product, because the vibration can take you in either direction. So it'll have values between 0 to 1. We're going to assume for the most part that kappa is pretty close to 1. Now, what about that equilibrium constant? you got to use statistical mechanics to deal with this, but we're not going to go into that. However, it does have a relationship in the same way that we remembered in the past that delta G equals RT natural log of K. We can use a similar relationship to relate this equilibrium constant to the difference in free energy between your starting materials and the activated complex. And we call this, we often call this the activation energy. All right, so this is how, we've dealt with reaction coordinate diagrams, or you've seen them before. You have your starting materials A and B, you have your products A, B. Here is the activated complex or the transition state, and this is the activation energy. And you've had this idea that activation energy, if it's higher, it makes the reaction go slower, and this is how that happens. The activation energy affects the rate constant. And in Eyring's formulation, the way it affects the rate constant is by affecting this equilibrium between starting materials and transition state. So we have the activation energy divided by RT, and then in front of the exponential we have a couple of terms that are necessary from the statistical mechanics point of view: Boltzmann's constant, temperature, Planck's constant, and then the vibrational frequency that we have here is going to show up there as well. All right, so if our rate constant equals little k with the double dagger times big K with the double dagger, and little k equals vibration times kappa, which we're going to assume is close to 1, and then big K double dagger is Boltzmann's constant times temperature times Planck's constant times the frequency times the number E raised to the delta G over RT. Our frequencies actually are going to cancel out. And we can rearrange all of this. And actually, depending on your units, Boltzmann's constant, and R are the same thing. Boltzmann's constant, I think, is per particle, and the gas constant R is per mole. So we can rearrange and say the activation energy equals minus RT times the natural log of your rate constant, K, times Planck's constant, divided by kappa times Boltzmann's constant times temperature. What we're saying here is if you measure the rate constant, you can derive the activation energy. If you know the activation energy, you can get the rate constant. So this is why we do kinetics experiments, is that we want to know the mechanism of the reaction. To know the mechanism, you've got to know the transition state structure and its energy, and then you can understand the rate of the reaction and how it happens. Okay, so that's a lot of math. What is the take-home message? Well, the rate of the reaction depends on the energy difference between starting materials and transition state. It also depends on this vibrational constant, which describes the vibration that takes the activated complex towards products. It depends on this transmission coefficient, which describes how often when you're up here do you go forward versus backwards. And then it depends on temperature. So you've heard that reactions go faster. Here's your rate constant, and here's our expression for the rate of the reaction. This is where temperature matters too, right? If you have a higher temperature, this quantity is going to be less negative. and so the rate is going to be higher. Also, temperature has an impact on the rate here. So this is why temperature accelerates the rates of reaction. But let's talk about that. We're going to generally consider, sometimes in thermodynamics, delta G itself can be temperature independent. We're generally going to consider, though, that the potential energy surface itself is independent of temperature, that you're not changing, by increasing temperature, you're not changing the energies of the starting materials versus the transition state versus the product. Instead, remember that we're thinking of temperature as a measure of molecular kinetic energy. And let's say this axis is population or probability of products having a particular kinetic energy. At temperature 1, that's low, we have that kind of distribution. So this is at temperature 1, where temperature 1 is going to be less than temperature 2. At temperature 2, we have another distribution. This is a higher temperature. And suppose that along this axis, the activation energy is here. So this is the activation energy to get over the transition state. Now the area under the curve, under each curve from this activation energy and on, is going to represent that percentage of the population of a molecule that has enough energy to get over the transition state. So at temperature 1, let's shade with, I don't know, we got to choose something, pink, fine. At temperature 1, we only have this much that has a high enough energy to get past the transition state. At temperature 2, though, we have a much larger amount, all of this. So that's how I want you to think about the influence of temperature on reaction rate. It's just an issue of shifting the population of molecules so that more of them have enough kinetic energy to traverse the barrier. All right.
Okay.
Yeah.
If we set temperature 1 is less than temperature 2.
Uh-huh. Good? Okay. What else? Okay, let's get to the issue of the Eyring plot, because that's something that's going to come up. I'm going to just rewrite our equation for the rate constant, which is something we can measure. And that's equal to this number kappa, the transmission coefficient, times Boltzmann's constant times temperature over h, Planck's constant, times the exponential of activation energy, the opposite of activation energy, over RT. Okay? And let's remember that activation energy is probably related to activation enthalpy and activation entropy, right? That's the typical definition of free energy. So each free energy is going to have an enthalpy part and an entropy part. So So for the Eyring analysis, we're going to take all of this and put it here. So K times H over kappa times KB divided by temperature equals the exponential of minus delta G over RT. Then if you take the natural log of both sides, you get this expression, which you can turn into minus enthalpy plus T times delta S over RT, or if we want to simplify that further, minus enthalpy over R times 1 over T plus entropy over R. So if I were to plot the natural log of my rate constant times the remaining constants here times temperature, if I were to plot that versus 1 over t, the slope of that plot is going to tell me about the activation enthalpy, and the intercept of that plot is going to tell me about the activation entropy. So if I measure the rate constant at different temperatures, that's the take-home message. If I measure the rate constant at different temperatures, I can get information about how much of that activation energy is enthalpy, which has to do with bonds breaking, bonds formed, and steric repulsion and electronic effects, versus how much is entropy, or changing in disorder, right? You might expect that in our reaction of A and B coming together to make an activated complex, you might expect that that entropy is going to be negative, right? Because you got to take two things and bring them together in a single activated complex. All right. We can also do this with relative rates of a reaction. And but I don't want to do that because we only have a minute left. So I think we'll stop it there. I'll show you next time how you can use measuring the rates of two related reactions to get information about how the change you made to a molecule changes the activation energy. Whew.